Applied Science Physics Unit number 3 Photoelectricity, X-ray and Laser. त्यामध्ये आपण फोटोइलेक्ट्रिसिटी एक्स-रे ऑलरेडी बघितलं, फोटोइलेक्ट्रिसिटी क्लासमध्ये झालाय. एक्स-रे लास्ट लेक्चरमध्ये तुम्हाला पीपीटी पण पाठवतात. टू स्टार्ट विथ ती लेझर. या लेझरमध्ये फक्त त्याच्या प्रॉपर्टीज आहेत, काही वर्किंग ऑफ लेझर, एक हेलियम निऑन लेझर आहे आणि त्याच्या ऍप्लिकेशन्स ऑफ इंजिनिअरिंग ऍप्लिकेशन असतील किंवा मेडिकल ऍप्लिकेशन असतील. मग अशी स्टार्ट केला होता. See, this is the full form of laser light amplification by stimulated emission of radiation. L for light, A for amplification, S stimulated emission radiation. आता exactly what are the properties? Coherent, monochromaticity, interaction, and extreme intense. Then the stimulated absorption, spontaneous emission, and stimulated emission. Exactly काय? That we consider by using the one video, small video ahe, that how laser works. Starting
maybe some of you have had unwanted hair removed.
Hope
or maybe you have built one and popped some balloons with it. Bottom line, lasers are ubiquitous not only in scientific research but also in industry. Just how do these little devices manage to put out that nice powerful collimated beam of light? All this and more coming up. As some may or may not know, laser is actually an acronym. It stands for light amplification by stimulated emission of radiation. However, nowadays it is so common that people don't bother to capitalize it and simply write laser. A very brief history of the laser starts in 1917 when Einstein introduced the concept of stimulated emission, which will be explained shortly. Then in 1954 the first laser was demonstrated by Charles Townes, the M standing for microwave. The ammonium laser was the first device based on Einstein's predictions and obtained the first amplification and generation of electromagnetic waves with a wavelength of about 1 centimeter, which is in the microwave range. This is recognized as the precursor to the laser. It wasn't until 1960 when Theodore Meyerman developed the first working laser at Hughes Research Lab. Meyerman's early laser used a powerful energy source to excite atoms in a synthetic ruby to higher energy levels. The development of the laser was a collaborative effort by scientists and engineers who were leaders in optics and photonics. Okay, so why are lasers useful? Why are they ubiquitous? The answer can be broken down to 3 unique properties the laser holds. The first being line width. The purity of a laser, referred to as the line width, can be quite narrow, more so than any other. Useful because many scientific experiments want to analyze stuff with certain energies. Different wavelengths of light correspond to different energies, hence having a source with one energy is helpful. The second is coherence. The light emitted by a laser is coherent light. This means it is all polarized in the same direction as well as being in phase. The laser is said to output highly coherent monochromatic light. An LED, on the other hand, is also monochromatic, one color, but it emits incoherent light. An analogy with synchronization and harmony can be made. Imagine an orchestra playing. If the orchestra is in sync and everyone is playing the parts correctly, it will be pleasing to the ear. The laser. If some players are playing out of sync but still playing the parts correctly, it won't sound as good. The LED. Coherence is important because all the photons add their energies together, and we can then focus them on a small spot over some distance. Lastly, power. Lasers make it possible to deliver high-intense light to a small area. Of course, militaries are particularly interested in this aspect of the laser, as well as medical applications. Laser eye surgery, for example. Now let's take a look at how a laser works. The workings of a laser are quite complex, as it requires an understanding of quantum mechanics. There are some commonalities behind every laser. The first part can be broken down to 3 key pieces: stimulated absorption, spontaneous emission, and stimulated emission, which is what the SE part of laser stands for. Let's take a look at the first concept, stimulated absorption. We will need a nucleus that is made up of protons and neutrons that has an overall positive charge, and is energy. Think of a ball on a hill and how easy it is for it to roll down. It wants to roll down because the energy state is lower, closer to the Earth's core than further away. In this case, potential energy. However, it is possible to excite electrons by some kind of external means. Just like we can exert a force on the ball that has rolled down and push it back up. Light can be this push to excite electrons. If a photon of light, which is 1 unit of light, comes across an electron in a low energy state, it can sacrifice itself and push the electron to a higher energy state. The photon is annihilated, but the energy of it is now part of the excited electron. It should be noted that each material has different levels of energy. In other words, if the ground state is 1 unit and the next energy level is 5 units, then the photon of light must have exactly 4 units of energy to excite the electron to that energy level. Anything lower will not suffice and anything higher would not as well, as there is nowhere for that extra energy to go, unless a higher energy state exists. If the incident photon is very high in energy, the electron would be ionized. To continue our analogy, it would be like trying to push the ball up the hill with not enough force. The ball would just roll back down. Too much force and it would roll down the other side, go to another plateau, or be launched into space. An exact amount of energy is required to elevate it to a particular energy state. Again, this process is called stimulated absorption, as we are stimulating the electron and it absorbs the photon's energy. The next mechanism we will look at is spontaneous emission. We now have an excited electron. What happens now? Well, again, this higher energy level is quite unstable, and after a very, very short time, about 100 nanoseconds of being there, the electron will eventually fall. For some perspective, light travels about 29 meters in 100 nanoseconds. When it falls back down, it will release a photon with energy equal to the difference in energy levels. The higher the fall, the higher the energy of the photon will be. Should the energy value of the photon that is released be in the visible range, we would perceive it as color. You may be thinking, if the electron reaches the higher energy level through the previously mentioned stimulated absorption mechanism, why exactly does it fall back down? Well, referring back to the ball example, imagine the ball on a hill, but now with the top having 0 friction and a sharp point. The ball can remain there only if it is perfectly balanced, but any tiny little force in either direction will cause it to start rolling. The electron in this higher energy state is in a similar situation. The forces that push it are small perturbations in vacuum energy. This is a quantum mechanical effect. Space or vacuum is not as empty as we think. Things are popping into and out of existence constantly. It is these vacuum events that perturb the electron. This is also responsible for why things are ferromagnetic. That's a different story though. Again, this process is called spontaneous emission, as the process that the electron falls back down to the lower energy state is more or less spontaneous. The last quantum process we will talk about, and the most important for lasers, is stimulated emission.
This is the main process of emission of laser light. That's a stimulated emission. Okay?
This occurs when a photon interacts with an electron that is already excited. This photon can act as a type of perturbation and force the electron to fall back down to a lower energy state and emit a photon. We then will have 2 photons. Photons actually like to be together. So if one comes near a situation where another one could be present, such as the electron falling back to a lower energy state, the situation usually will play out. The important part is that the emitted photon will be identical to the one that stimulated it, meaning same frequency, phase, and polarization. They will be coherent with each other. So, if we could somehow avalanche this process, we would have a laser. After all, that is basically what a laser is. A zillion identical coherent photons being emitted. In contrast, if two electrons undergo spontaneous emission, the emitted photons will unlikely be traveling in the same direction, nor be in phase. But in order for electrons in the excited energy level to be able to undergo stimulated emission, and not spontaneous emission, enough time has to be available. The lifetime of an electron in the excited level is just too short. However, some materials have so-called metastable states. These are excited states with slightly lower energy than the excited states. These states allow the electron to remain there for much longer lifetimes, milliseconds instead of nanoseconds. Enough time that a passing photon can cause it to undergo stimulated emission. Of course, an initial spontaneous emission from the metastable state to the ground state must occur in order to have the initial photon that can stimulate other excited electrons in the metastable states. To sum up, if a ground state electron is hit with a photon, it will absorb it and move from the ground state to the excited state. The photon must have the energy equal to the difference between these levels. This electron will then transition to the metastable state, if one exists. This transition does not emit a photon, and is said to be a radiation-less transition. The energy difference is dissipated in other ways, heat or phonons. Now this electron, if a photon stimulates it, will emit a photon with equal energy, phase, and direction. These are the ones that make up the laser beam. It should be apparent that the photon which pumps the electron from the ground state to the excited state has a different energy than the photons that are being lased. This is because the energy difference between the ground state and the excited state is different than the difference between the metastable state and the ground state. The pumping photons are always higher in energy than the photons being lased. We obviously want lots of electrons in this metastable state, more so than the ground state, in order for them to be in a situation where stimulated emission can occur. Something known as creating a population inversion is required. If we only had two levels, we would reach a point of saturation, where 50% of the electrons are excited, and 50% are not. The excited electrons simply spontaneously emit too fast. Essentially, our medium becomes transparent to photons. By introducing the metastable state, we force the pumping photons to excite the ground state electrons, that then transition to the metastable state. So the photons that are emitted by the transition from the metastable state to the ground state are primarily used to stimulate other electrons in the metastable state. Enough time exists for this to happen. Yes, some of these photons will excite ground state electrons directly into the metastable state, but the pumping photons should take care of the majority, and create a situation where there are more excited electrons in the metastable state than ground state electrons, a population inversion. By the way, the above is describing a 3-level laser. 4-level lasers exist and are more efficient. Again, we want to create an avalanche effect, where the spontaneously emitted photon that was created when an electron transitioned from the metastable state to the ground state gets amplified through the means of stimulated emission. We don't want just a single puny photon, we want lots, all working together. It is not practical to create a laser that is extremely long, so the solution is to put the laser medium in a cavity. Let's take a closer look at how a cavity will influence the light waves, and how exactly this will create the amplification we desire. Since light is a wave, it will be subject to constructive and destructive interference. We want constructive interference in our cavity to take place, in order to have a high-intensity beam. A laser cavity has a mirror on one side and a partial mirror on the other. It is partial because we want some of the beam to escape. That's the beam we see. Now, when light waves are created through spontaneous emission, they will initially travel in random directions. But the ones traveling perpendicular to the mirrors will reflect back and forth. Let's take a look at one of these light waves. It is first emitted via spontaneous emission and quickly becomes large in amplitude through stimulated emission. It travels towards the mirror and is reflected back. Because we continue to stimulate atoms in the left and right directions, we get two waves in the cavity. Again, one moving to the left and one moving to the right. Waves will add their amplitudes when interfering with each other. In this case, we will get a standing wave. Meaning instead of a wave noticeably moving to the left or right, the combined wave will appear to be going up and down. Rest assured, this is just an illusion. This is the effect of two waves hitting each other head-on, and their left and right components cancel out, but their up and down components add together. So when the wave looks flat, this is a moment when the two waves are destructively interfering with each other, and at the maximum they are in a constructive interference point. Here are a few examples of some standing waves in a cavity that are resonating. Resonance is just a fancy word for having these waves being in a state where standing waves are being produced. A mode being just what n you have. N equals 1 is a mode, n equals 2 is another one, n equals 3, etc. Is there an equation that will tell us what modes can exist in the cavity? Sure there is. The left part is the frequency that exists in the cavity. N is the mode, which is always an integer. V is the velocity of the wave, and L is the distance between the two sides of the cavity. The velocity in our equation is the speed of light, c, which is 300,000 kilometers per second. The L is just the distance between the mirrors. Light traveling from the left of the cavity will now interfere with light traveling from the right. So again, we have these possible modes where the light can produce standing waves and be in resonance. Not all frequencies are able to exist in a cavity, but a lot are. Also, let's be clear that the standing waves produces are a collection of trillions and trillions of light waves all working together. They are produced by stimulated emission, and the cavity allows them to keep amplifying each other. They are coherent with each other. Recall, this was one of the big reasons why we care about lasers. If we didn't have this synergy between light waves, we would just have an ugly LED. I bet you can't make your cat go crazy with a red LED. Well, maybe, but you get my point. Question: what frequencies are allowed to exist in a red laser pointer's cavity? Answer: a cheap red laser pointer has a cavity length of about 1 millimeter, and the speed of light is c, 300 million meters per second. Plugging in these values to our equation, we would get a difference between allowed frequencies of about 150 gigahertz. Now, red light has a frequency of about 400.05 terahertz, which
this just एक working of laser दाखवलं त्यांनी, starting with our PPTs मध्ये spontaneous emission, stimulated emission and spontaneous absorption. याच्यात त्या 3 टर्म होत्या with one more term. See, ही एक टर्म होती population inversion, means making population of higher energy level than lower energy state. पूर्ण डिटेल मध्ये त्या व्हिडिओ मध्ये दिलेलं आहे तुम्हाला. that video I will share again. Optical pumping is another method to emit the laser light. Optical means by using the light we are emitting or we are generating the lasers. After that, helium neon laser is there. In your syllabus, helium neon laser मध्ये आपण प्रॅक्टिकल मध्ये बघितलं होतं बघा. That was a helium neon laser. The principle is light laser light emitted by application of high frequency current to helium neon gas mixture. आता याची तुम्हाला ट्यूब दिसते. This is also one construction. जैसे construction है. This helium neon laser consists of fused quartz tube having the length 80 cm and diameter of the 1.5 cm. ही जी ट्यूब आहे, ही ट्यूब आहे is about 80 cm long असते with the diameter 1.5 cm. यामध्ये mixture असतं helium and neon gas. That helium neon gas mixture, 10th part is of helium and 1 part is of the neon. And perfect reflector is fixed at one end. या साइडला जो perfect reflector आहे, and one side is a partial reflector. यातून laser light pass out होते. And that whole the tube is attached with the high frequency generator, and that is active material excited by means of the high frequency. It means या ट्यूबच्या आउटसाइड आपण काय करणार आहे, एक हाय फ्रिक्वेन्सी अटॅच. बिकॉज ऑफ दॅट एक्साइटेड ॲटम ऑफ हेलियम अँड निऑन गेट एक्साइटेड. लास्टली त्यांनी एक जस्ट फॉर द नेक्स्ट साइड वर्किंग ऑफ हेलियम निऑन लेझर लेअर, एनर्जी लेवल डायग्राम तू एक्सप्लेन केलेलं आहे. एनर्जी लेवल लेफ्ट साइडला हेलियम ॲटमची आणि निऑनची राईट साइडला. यामध्ये when electric discharge is produced in tube, helium and neon gas atom are excited. Some excited levels of helium are close to some excited level of neon. Therefore, this excited helium atom collide with excited atoms of neon and transfer the energy to neon. Because helium's second, third is the close to excited neon fourth, neon sixth level. ज्यावेळेस हेलियमचा थर्ड इज द कोलाइड विथ द निऑन 6-1, दिस निऑन atom goes to the ground state with means excited helium is incident on the excited neon. हे जे neon atoms आहेत, that neon atoms is triggerly stimulated to the lower state, and because of that lower state laser light will be emitted. The second part मध्ये actual lasering action done by the neon atoms, and these neon atoms with extra large energy from helium are forced to jump to the ground state by emitting the photon. This produces the laser light. Newly emitted photon is next neon atom and increase the radiation. Simply the laser light जी produce होते that have the same properties, coherent, monochromatic, unidirectional, and so working. See, after that the engineering applications of laser. आपण याचा एक व्हिडिओ पण बघणार आहोत, how the engineering applications. आता engineering application मध्ये lasers are used for engraving and embossing the printing plates. For example, number plates and the plates. And that laser used in cutting, drilling, and welding the metals. Lasers are used in holography मध्ये, computer printers से 3D laser scanners. It's also controlled to heat treatment, data transfer to the computer, surgiless eye treatment, surgiless treatments of different bodies part and scanning of different. See, if we share one video, एक small video है to the applications of laser. See, start the uses of 15 uses of lasers are there. We have the 10 minutes.
In this video, I'm going to be talking to you guys about some of the practical, real-world uses for lasers. I'm going to be doing 15 uses for lasers, and this video is mostly in response to a lot of comments that I get on my laser videos saying things like, what do you use lasers for? What is the real use besides just pointing it at the ground for your cat or just messing around with it to burn stuff? What are the real-world uses for lasers? So I wanted to kind of do a nice little compilation video to kind of explain some of the real-world uses that people are using lasers for today in different industries. This list is definitely not all-inclusive. There's a bunch more laser uses that I was not able to include on this. I just included 15 that I thought were pretty interesting and that some of you might not have heard of. And it's in no particular order besides number one, just because number one's kind of my personal favorite. And that is laser photogrammetry, and I'm hoping I'm pronouncing that correctly. And it's basically a method to measure large animals underwater without having to physically take them out of the water or hold a long, say, rope or measuring device up along the side of them, hoping they hold still. This method involves mounting two lasers basically on parallel lines, and it involves a lot of precision and a lot of tweaking to make sure these lasers are on precise parallel lines so that the dots would, say, be maybe 1 foot apart from each other at all distances, or at least within a couple hundred feet. You would then aim the 2 dots at the side of an animal, say this whale shark, and take a picture of the entire animal with the 2 dots on it. And you can then look at that picture and say, these 2 dots are a foot apart. How many of those little spacings can we fit on this one picture right here? And that'll give you a pretty accurate size of the length of the animal, a lot better than just eyeballing it. Lasers also have a big place in astronomy. The images that you're seeing right here of these yellow lasers coming out of observatories, these are sodium lasers which are being used to create guide stars, basically doing a reverse distorting of the atmosphere so they can get a clear picture of what's beyond our atmosphere. However, the process is a lot more complex than that short little summary I just gave you. Lasers are also used on the satellites that scan Mars and the topographical maps they create of Mars. Lasers are used on board those satellites, and we obviously also use lasers for stargazing and for pointing out different constellations in the sky. Use number 3 is laser levels, and these type of construction tools will allow you to generate laser lines on walls or surfaces to create a more accurate level, get perfect 90-degree angles, and other construction purposes with absolutely perfect lines that you wouldn't otherwise be able to get. Use number 4 is the medical field, where lasers are used for a wide variety of things, including LASIK surgery, dentistry. They're widely used in tattoo removal. You see them used a lot in MRIs and different types of scanners, and they're also widely used in skincare. Lasers of different wavelengths have a lot of uses in the medical field. The 5th use is data transfer and communication via fiber optic cables. So the concept, I'm going to simplify it as much as I can here. Imagine you have a cable, a wire that is hollow on the inside, and all the walls on the inside are very reflective, like a mirror. If you were to shoot a laser into this wire, the laser beam would just keep bouncing off the inner walls of the wire, and it would come out the other side. It wouldn't just stop inside of the laser. If there was a turn, it would just keep bouncing and following the wire until it came out the other side. And we are using these laser lights to send information and communicate, and that communication is now being sent at the speed of light, much faster than previous ways of transferring data. Now, it's obviously a lot more complex than that, but that's just a very simplified version. Number 6 is going to be laser tag, and this one's pretty simple and straightforward. I'm sure most of you have played it in the past. It just involves using lasers to shoot at targets on your enemies. Usually they'll be wearing some type of a vest with a target on the shoulders, back, and chest. If you hit those little targets, the enemy will be disabled for a couple of seconds, and you'll get a point or 2. Use number 7 is materials processing, and this is just kind of a blanket term I use for the different uses of manipulating material with lasers. This can be engraving, this can be lasers used for drilling, lasers used for cutting items like metal. There's also lasers used for removing rust, and there's also lasers used for welding. Now, the lasers used for all of these uses are typically in the invisible spectrums and also very, very high powered and would burn your skin immediately. And that leads me to number 8, which is military uses. The military has actually for some time been working lasers into their weaponry, using laser systems to shoot down drones, shoot down planes, and shoot down missiles. And they began mounting them on ships, on trucks, on planes, and these lasers are also very high powered and have the ability to go straight through metal. Use number 9 is one of the more obvious and conventional ones that's been around for a while, and that is the use of laser diodes and disk drives to read DVDs and CDs inside of your DVD player or your Xbox or whatever it might be. Inside of any of those devices that take disks, there will be a little diode with a little laser that is being used to read that disk. Use number 10 is in the agricultural field, and it's the use of lasers as a bird repellent or deterrent. Now, farmers have been installing these type of automatic laser systems on their crops, and birds will actually view that laser beam and that laser dot as like a solid rod coming towards them or a stick coming towards them. They won't be able to identify that it's just light, and it will immediately scare them away. Use number 11 falls more under the scientific field, and this is optical tweezers. The focal point of a laser can actually be used to trap microscopic little particles in the air, using just the force of light to suspend them in the air. It's a pretty interesting process, and I'll link several demonstration videos that people have done down below in the video description. Use number 12 is the use of lasers as gun sights. A laser can be perfectly aligned with the barrel of a weapon so that you can get a more accurate idea of where your bullet is going to land. Use number 13 is something you see in pretty much any grocery store, and that is those little barcode scanners. Those actually have a laser inside of them that's producing that moving light that you see going over the barcode. So basically, the barcode scanner has a illuminator in it, which in this case would be the laser. It sends out the light at that barcode, and then some of that light reflects off of those little black lines, and it goes back into the scanner, and the scanner has a sensor that then decodes it and tells the scanner what the barcode actually said. Number 14 is a laser printer, and inside of these type of printers, the computer board will come up with whatever the image is supposed to look like, whether it be text or a picture. It'll tell the laser inside drum owner that is supposed to be. Entertainment such as laser light shows at concerts, and I think that some laser pointers would also fall under this category, as many people do own them for the sole purpose of entertainment. But anyways, that's going to wrap up my 15 practical real world uses for lasers. If you guys
This again meeting timing. Countdown close in 1 minute. ठीक है, मी तुम्हाला व्हिडिओ पीपीटी पाठवतो ऑफ दिस लेझर अगेन, आणि मूल टेस्ट पण सॉल्व करायचे ऑफ लेझर. अपग्रेड सांगत आहे स्टॉप मीटिंग हियर. ठीक आहे, रिमेन स्टुडंट मूलच्या टेस्ट सॉल्व करत आहे. ठीक आहे. नेक्स्ट टाइम दा नाव चेंज करा. एलजी स्टाइल कौन है रे? मीटिंग विल क्लोज. ठीक है.